So what do we see the last class? We are seeing it. We are getting the Bernoulli's equation here. So after the Bernoulli's equation, what are the assumptions? We just recap to get the Bernoulli's equation. Again, assumption is much more important here. So we rewrite this assumption again, and we'll thinking that what is the physical meaning of this equation? What does it want to tell it? So the first assumption, we are taking it here. Inviscid. First assumption we are taking it. Second assumption we are taking it that gravity is only body force. Is only body force. Third assumption, we are discussing about the steady flow. But Bernoulli equation, there is the unsteady Bernoulli equation also. We can write it down, the unsteady Bernoulli equation. We'll write it after some time. But whatever we are going to write it now, that is a steady flow equation. So P1 plus rho g plus V1 square by 2g plus Z1 is equal to the same way, P2, same subscript with the 2, the same terms. That is the only applicable for the steady flow. Next, the fourth one. The fourth one is we are taking it. Fourth one is a two-part. Two-part is a condition or this part. So V cross del cross V dot dl to be 0. So what are the condition is required? Either along a streamline, the 2 points we are choosing, we are differentiated. Whenever we are going to perform the integration, we are taking in between 2 points, not 2 sections. This Bernoulli equation is only applicable in between 2 points, not in 2 sections. This thing you have to keep in mind. So 2 points. So these 2 points should be either along a streamline or the entire flow field is the irrotational flow. The entire flow field is the irrotational flow field. That means curl of velocity vector is a null vector itself. That is the fourth assumption. And the fifth one is constant density flow. So density is not changing with the cross section or anything else parameter. So after satisfying all assumptions and doing the integration in between 2 points, very important terms it is, in between 2 points. Whatever the equation we are getting it P1 by rho g plus P1 square by 2g plus 0. That should be equal to the P2 by rho g plus V2 square by 2g plus 0. This equation, most popular equation, is the Bernoulli's equation. But we cannot apply Bernoulli equation in everywhere. Before applying the Bernoulli equation, we should check this assumption whether it is satisfied or not. If it is not satisfied, Bernoulli's equation you cannot take. Just like wherever you want, you can apply Bernoulli's equation. It is not. So you have to first check whether this assumption can be taken or not for a regarding flow field. So that is the most important thing for these cases. But what is the physical significance of this Bernoulli's equation? What is the physical reflection? What does it want to tell? So 3 parts of this equation. So simply we can write it down. P by rho g plus V square by 2g plus Z is a constant. So P by rho G plus V square by plus Z is a constant. Rho G plus V square by 2G plus Z is a constant. What is that? This part. This is all head. Head means the energy head. That means energy per unit weight. Unit weight. Energy per unit weight. That means energy. What is the energy equation? Take it. Let you take this, the kinetic energy per unit weight. Kinetic energy per unit weight. How it is coming? Kinetic energy equation we know half mv square. Kinetic energy equation half mv square. Per unit weight m into g. Weight is the mg. So that is come v square by 2g. So energy per unit weight. So this is the kinetic energy per unit weight. This is the potential energy per unit weight. Energy per unit weight. So potential energy we know mgz or mgh. Mgz you take potential energy divided by the voltage. So there's the potential energy per unit weight. What does it mean by this term P by rho G? So this is called, another name is called the kinetic head. This is known as the potential head. This is known as the pressure head. So pressure head, loosely we are telling it, pressure energy per unit weight. Pressure energy per unit weight. So loosely we are telling it. But in case of the thermodynamics, if you say here, the thermodynamics, the knowledge we are saying, over the pipeline, if you want to maintain one flow against a pressure P, you want to maintain a flow against the pressure P. So here the pressure, pipeline pressure is the P. Against this pressure, you want to maintain some flow. So you have to do some work. To maintain the flow, whatever the work you have to done, this work is known as the flow work. So to maintain a flow against a pressure, how much work you have to do, this work is known as the flow work. So let the area is taken as the dA is the area. This area is the cross-sectional area is the T. So what is the force? Force is P into D. Magnitude, we are talking about magnitude here. P into D. And because of this case, how much displacement occur? Let the displacement is taking dx or del x. Displacement is dx or del x. You can write it in del term also. It's better to write in del term. So let you take the area del A, and this is the del x. So this is it. So the work done, P dot del A is the force into displacement. Del x. And what is the weight of this element? Flow work per weight. So weight of this element, weight is the rho density of the fluid into volume. So volume is del A into del x. That is the volume into G. So mass into G, that will gives you the answer. So del x and del, this will be cancelled out. Remaining part is the P by rho G. This P by rho G is nothing but the flow work per unit weight. This is the thermodynamically we can say that is nothing but the flow work per unit weight. That is the physical significance of it. So pressure head is nothing but that is the flow work per unit weight. So what are the equation? We are writing it here. The first, the pressure head term. Pressure head term is coming to create the flow. So pressure head is flow work per unit weight plus kinetic head, kinetic energy per unit weight plus potential head. So these three combinedly is known as the mechanical head. Mechanical energy per unit weight. Mechanical head. This is the mechanical energy per unit weight. This is a combinedly, we can tell it. So P by rho G, P square by 2G, and that is the J. So that is the mechanical energy. So this assumption, mechanical energy is a constant. Mechanical energy is a constant when it is an inviscid flow, steady flow, then inviscid fluid, steady fluid, constant density flow. Again, whether it may be a rotational or there is a chances of getting the along a streamline. And gravity is only body force. So this is the this condition will be satisfied whether the assumption is true. All assumptions are true. Then Bernoulli equation can be applicable in between 2 points, point 1 and point in between 2 points. So whenever you are going to apply Bernoulli's equation, either you have to consider along a streamline, that the streamline is like that way, then you can apply Bernoulli's equation, or the flow might be irrotational flow. So in that case, this is a constant. So along the streamline, if you consider along the streamline, so mechanical energy always will be conserved, constant. Always it will be constant. So this is the physical reflection of the Bernoulli's equation. Three part of the Bernoulli's equation. One is the pressure head, kinetic head plus potential head. So this is nothing but whatever we are discussing, that is the physical reflection or physics behind the Bernoulli's equation. You can write it down. Physics behind the Bernoulli's equation. There may be separate Bernoulli's equation for the unsteady flows. If the flow is an unsteady flow, we can apply Bernoulli's equation also. So unsteady term will be here. In that case, if unsteady flow Bernoulli's equation, along a streamline, if you consider, along a streamline, if you consider, two part, either it should be along a streamline or irrotational. So if you consider along a streamline. So along a streamline, let the streamline is a ES. Along streamline, the unit vector, we are taking it ES. So any velocity vector, we can write in magnitude into unit vector in this way. And DL vector, length vector, so along streamline DS into, DS is the magnitude into the direction, both are the same. So as it is the unsteady, so this part will not be zero. Which part? Del V del T dot DL. Rho del V del T. This part will not be zero. So these some values will be there. So what are these values? Del V del T into ES DS dot ES dot product. So ES will be 1. So simply the vector will be becomes a scalar quantity. along a streamline. This is the extra part will be with the equation. This part will be the extra with the equation. So what your equation previously? Del P plus half rho dv square plus rho g dz plus one extra part will be here. Extra part will be the Euler equation we write. In case of the Bernoulli's, 1 to 2, if you apply integration, it will come after doing the integration. So that will be some values. So you can write it down, P2 minus P1 plus half rho V2 square minus V1 square plus rho G Z2 minus Z1 is equal to rho del V del T ds plus 1 to 2 is equal to. So hence, a simple equation can write P1 plus half rho V1 square plus rho G Z1 is equal to P2 plus half rho V2 square plus rho G Z2 plus one extra term, unsteady term will be present in here. For the case of the along the streamline. Here only remaining term is the unsteady part will be, this part is the unsteady part. So this part will be 0 when the flow is steady. And here you could be able to understand is the unit vector along the streamline. So ES is nothing but we are telling unit vector along streamline. Whenever we are discussing about the streamline coordinate, you can see the ES is along the streamline and perpendicular to the streamline another coordinate. Just like X and Y, we are taking it in this. We'll discuss just same thing, just conceptually I'm telling it. So along the streamline, we are taking it ES, and perpendicular to the streamline, we are taking it EN, unit vector. Just like I and J. I we are taking along X-axis and J we are taking along Y-axis, the same one. Along the streamline, perpendicular to the streamline. This kind of the, taking this kind of the coordinate is known as the streamline coordinate. What is the advantage to taking the streamline coordinate? Because we know the definition of the streamline is such an imaginary line where you draw from any point, if you draw a tangent, that will gives you the velocity. That means the velocity is existing. The velocity is existing only along ds. Velocity is existing only along ds. Yes. So along En there is no velocity. So it seems like a one-dimensional velocity at any instant. It seems like a one-dimensional case. So it is a most easier. So if there is a two-dimensional velocity, so two-dimensional case, we can reduce the problem in terms of one-dimensional if we use the streamline coordinate. That is the advantage of taking the streamlines. So that's only the cases. So first we are taking along the streamline. If it is a rotational, e-rotational flow, if it is a e-rotational flow, then what will be happening?